Welcome again to this second lecture. As I told you, this one is recorded. Keep asking questions. I said it already, but keep asking questions at any time, and we'll have the normal breaks and the topic of the course. So, what are we going to see today? As a reminder, last week we have seen the pre-processing steps. And as I told you already last week, at each of my lectures, I will remind you the typical structure of an image analysis problem, an image analysis algorithms. Basically, you will start with raw data coming from sensors. And this is what you get from electronics, sensing, and optics and things like that. What those sensors give you is basically raw data. In imaging, I will call them stupid pixels. They are just points in a matrix, as we have seen last time. And the goal of what we will see today is how to transfer those stupid pixels in something a little bit more meaningful for your application. This is what we will see today in terms of segmentation. What we have seen last time is basically how we can prepare this, how we can improve the quality of an image, how we can denoise, how we can restore, how we can stretch, geometrically transform an image. Okay? That's what we have seen, very briefly of course, but I think with that you have the foundations for doing the pre-processing, at least for understanding more advanced pre-processing techniques. What we will see today is basically this. We will go from stupid pixels to a little bit more structured information. And when we will have that, next time we will see how to describe those. What we will have here will be called objects, in a very natural sense of the term. And we will describe them by features. So from objects we'll go to features. Features are just numbers in a vector. How many we'll see. And from those features, from those vectors, we will do classification, call it artificial intelligence, call it machine learning, whatever. This is basically what we will do in the third lecture from now. So basically, today we are going to do image processing, but after that, images will be gone. We will work with basically objects, shapes. And then after that, shapes will be gone, We will use vectors and we will use artificial intelligence, machine learning, whatever. Of course, I will not go in any of the details of those topics because, of course, each of them could be a course, and indeed, for instance, machine learning is a course by itself. So I will give the foundations here. And at the end, with that, you will be able to do something, which is a decision or an action. And that is out of the scope of this course again. Okay? Clear, huh? I think it's pretty simple. Okay, so let's go with the segmentation today. What is the problem that we want to face? Basically, I will use this very simplistic image, but it looks like something that you might have to do in an industrial context. You want to recognize something. So you get an image. In this context is a simple grayscale image where we have a nicely bright background and nicely dark objects in the natural sense of the term. And obviously what we want to do is to something, recognize, extract, count, whatever, okay? So basically we have those stupid pixels and we are interested in the content of the data. So we'll try to extract the objects. And the objects, in a more precise definition, is the part of an image which has a semantic meaning, which is semantically coherent. An object for me here might be all those black pixels. But they should be, I mean, this is an object, this is another. For another application, it could be, I don't know, the object is the keys and the rest is the background. It very much depends on the application, of course. But still, as a very first definition, an object is a semantically coherent part of an image. Okay? And that's what we want to extract now. So now look at that. How are we going to do that? I would like you to participate in this course by basically putting ideas on the table. Right or wrong. I don't care, and you don't have to care whether you put good ideas or bad ideas. We will discuss that. But I want you to participate. Just try to imagine how you will teach an algorithm, or how you will write an algorithm to extract those objects. It's very simple, right? In this case, you want to extract the objects from the background. You will basically use the intensity, the gray level. What other idea could you have? Can you propose something else? Yes, please. Right. So in the The frequency is a strange term here. In the contrast, let's say. Huh? Okay? So I repeat for the mic. So sudden changes in the intensity, if I phrase it correctly, somehow. You were mentioning frequency. Well, frequency is at high frequencies, if this is probably what you had in mind, because a sharp transition is a high frequency. So you somehow had that in mind. But a sharp transition, that's very good, thank you, because it's the second part of this course. Well done. So we prepared that very well. No? No. So basically two types of IDs. Grayscale, you define the content of an object by its appearance, or transition between one appearance and another. Yes, please.
We could use histogram-oriented gradient to...
Sorry, so you use what?
Use algorithm
yes?
to define the object.
Absolutely. Which one, for instance, you said?
Histogram-oriented gradient.
Okay. Oh, that's another story. If you want to recognize the objects, you will have to describe them. And here he was mentioning the histogram of oriented gradients, the hogs. So this is a feature that you can extract from that to characterize an object. Here I am one step before. I want just to describe it. Of course, sometimes you can skip this. I want to extract it. I said describe. You want to extract it. Of course, sometimes you can skip the extraction and directly describe the content. We will see that in the next lecture. But here, my task is just to extract the objects, okay? So basically two types of methods that we already tried to identify. Those describing the object as their content, their appearance, and those describing the object as something that is surrounded by a transition. And this is exactly the two chapters of this course. And the two types, the two families, and there are no other, the two families of segmentation. The first ones are region-based methods. The second one are contour-based methods. And we will see both today. First chapter, region methods. Second chapter, contour detection, contour extraction, okay? Okay, so that's very good. So in this case, indeed, you can define the object as, for instance, something that is connect with a coherent color appearance. That's basically the region methods. Or you can say, indeed, they are surrounded by sharp edges. That's the edge detection methods, the contour detection methods. So that's very good, and it works for many, many, many applications. If you have to extract something from an image, you might want to use either the region-based methods or the contour-based method. And that is very general, and that works very well. Of course, there are exceptions. This is a real image, but pretty simple. Now look at this one now. Okay? This is my kid, the first one. He was 15 years old yesterday, but still. Now try to extract and measure the size of this baby. Connex object, boo. Okay. With coherent color, boo. Surrounded by sharp edges, boo. Okay? So, what I say here is not the truth in all the cases, of course. You can also have more subtle definitions of an object, like coherent texture, the appearance, the texture of the image, not the pixels themselves, but more like statistical information about the region. You can have also prior knowledge. When you see that, you recognize first that this is a US image, an ultrasound image, an echography. And very naturally, you know that echographies are used mainly to diagnose and monitor babies, fetus. And so basically you recognize them because you know what you want to recognize in that image. So using prior knowledge is a large part of the research and image processing, of course. This is not part of this course, no. Okay? So that's what we are going to see, not that, but rather that. And this one will be our, our example for the rest of this course. So we are going to extract objects. So we are going to do segmentation, which is the partition of an image between objects and background. And hopefully, it should be a complete partition and a unique partition. We don't want to have overlap. An object is not both in the background and in the object. Okay? And so regions and contours. That's basically what we'll see. And these are the two chapters of this course. Okay, first, let's do it very simple. But you will see that we can do very nice mathematics already with extremely simple methods. And you will see that simple doesn't mean that it doesn't work. It's really like solving most of the problems that we have, at least part of it. Obviously, in that image, a very simple way to distinguish the background and the foreground is the intensity of the pixels. And here I already have a comment. If you want to do an image analysis task, and if you can play with the image acquisition, please do it. You can recognize those objects on a complicated, cluttered background. You can put them on a scene anywhere. But you can also prepare your setting in an industry, for instance, in a production chain, so that the image is clean at the acquisition. So first message, please do everything you can at the acquisition level. It will simplify your life. Now we have that image. We want to work, and the very simplistic way to extract the objects is to say, okay, the objects are dark and the background is bright. So the question is, can we define a threshold? A threshold in the range of gray levels. Below the threshold, well, in this case, below means dark. So below the threshold, it would be the objects. Above the threshold, it would be the background. What is written there is the opposite, because normally we say 1 is the foreground and 0 is the background. But that doesn't matter. So basically, we have a threshold, and on the one side of the threshold, in the range of gray levels, we have the objects, and on the other side, we have the background. And so the question is how to set the threshold. This looks like an extremely simple question, but you will see that we can have a very strict and very precise definition of what is the best threshold. And obviously, if we find the best threshold, it will work very nicely. But if you don't find it, we will have problems. In this case, the threshold was set to too low or too high. If it's too high, remember that black is low value and white is high value in the gray level. Huh? So if you set the threshold too high, you will have many pixels that are classified, defined as foreground, because low values are foreground. So basically, this is this case. This one has a threshold which is too high. Pixels that were actually quite bright but not bright enough were below the threshold. And the opposite. This is a threshold that is set too low. Okay? So how to find it? Well, obviously you can tune. But in an automated process, it doesn't work. And so basically what we are just going to see now for a few minutes is something that looks trivial, but how to set in a principled way the best threshold. And what is the problem that we have to set this threshold? What is the main problem that we might have when defining the threshold that we have to fight against?
For some objects it will be fine, but for some others it will be something that's not right.
Yes. So, of course, if the image is not a binary image or a bimodal image, of course it will not work. I guess that is what you mean. But in some cases, you might even not find a threshold that will separate perfectly the two types of objects. Why?
Non-uniform background.
Non-uniform background, yes, indeed. So that comes to the same. If you have a non-uniform background, of course, your gray levels will not be nicely split between background and foreground. So you're right. Then you might have to work more locally. The main problem that I want you to recognize is the presence, even in that setting, is the presence of the noise. Because if you have a lot of noise in your image, some of the pixels of the foreground, because of the noise, will be artificially bright, locally, and some of the pixels of the background, because of the noise, will be artificially dark in this case. Okay? So we'll have to fight with that. And a good way to analyze the content of this image in terms of its gray level is obviously what we have seen last time, the histogram. We have seen a histogram is equalization last time. So basically, if we look at the histogram of that image, basically, you will see that it is kind of bimodal. You have a large number of pixels that are dark and a large number of pixels that are bright, and in the middle, a little bit of noise. But that's what we will see in a minute. Before that, we can also identify some of the problems where definition of the threshold is trivial. And this is real and practical. For instance, if you acquire images for which the gray levels have a physical meaning, it might be in optics, it might be in X-ray, it might be in magnetic resonance, might be in many modalities where the gray level has a physical meaning. This is the example of a computed tomography, which is X-ray, where the gray levels represent actually the density of the medium. An X-ray will not penetrate deep in a dense medium and will go through a non-dense medium. And so, I will not explain how, but basically we reconstruct CT, computed tomography images that depict the density of the medium. And then when we have that, it's simple because it has a physical meaning. If I want to extract the bones, I know that the bones are dense. With a certain density, I set my threshold just below that, and I get my bones. And I don't have to look at the images. I know the value that corresponds to the objects I want to extract, and I extract it and do a nice rendering and diagnosis and what you want. So that's okay. But for most of the methods, we don't have this prior. We get an image which is taken by a camera or by an industrial inspection system. And basically, the only thing we have access to is the pixels. And with the pixels, we can draw the histogram. Okay? And that's what we are going to work for the next, say, 10 minutes or so, with the histogram. So as I said, if we look at the histogram of my image here, it looks like that. You have pixels that are dark, and you have pixels that are bright. And that's it. And you have to use that to define the threshold. Okay? So now I would like you to come with ideas how to define the best thresholds. And please put ideas on the table and we will discuss them, and you will see that you are probably right in some cases, but you might be wrong in other cases. It's okay, right? It's not the interviews yet. Yeah, 3 that follows. That's good. Ideas. How to define the best threshold for segmenting that image. Please come with 2 or 3 ideas. Don't bother whether they're right or wrong. I just want ideas. Yeah.
Could search for an accumulation of similar thresholds and then, for example, define a mean.
Okay. How do you define those different thresholds? Yeah, but what? My point is, you have that. What do you analyze? What do you want to extract from this histogram to define those thresholds? I agree with you that you can have different trials. But how do you define a possible threshold?
We want the low intensity parts, right?
Yes, we want the low intensity.
We can just try a bunch of different thresholds that separate the most low intensity parts from the
Yeah, but you don't know whether you are right or wrong. If I put the threshold here, it will separate, indeed. I don't have the ground truth. But I see the histogram, though. And the histogram is nicely bimodal, clearly.
So since we have those 2 peaks,
yes.
we know that there are 2 different regions.
Yes.
Try to put the threshold maybe in the middle of the
Very good. Thank you very much. So first idea, and we'll see if it's good or not. First idea is something like it should be here. And here it's something in between the 2 main peaks. Another idea. Yes. Sorry. Yes.
Maybe like in the middle, what we see is actually noise, like it's flat. So we can say this is roughly the noise level, and hence we have to put the threshold at the point where it's right above that.
Yeah, something like that. Huh? So it might be somewhere here, but why not just in the middle? Because that's what separates best. That's not exactly, yes, that's what you said. Just in the middle is the mean between the peaks. What you said is, okay, this looks like the contributions of the noise, so maybe somewhere here or somewhere here. Okay, I get that point. I don't say if it's a good idea or not, but yes, last one, and then we stop.
You can minimize the L2 norm from
Between what?
threshold,
Between what and what?
from the threshold and all the intensity of the...
Okay, an L2 norm will basically calculate the mean square of the intensities, right?
Yeah.
Okay, that's a possibility also. Something like an average, well, another way to calculate the mean. That's what you mean? Okay, good. Okay, maybe one last one, because I still want to have one of them. Yes?
Could we make some assumption on the noise?
Okay, and I stop you, otherwise you will give the answer and I don't have anything to say, but you're right. Can we have an assumption on the noise? And now I want to explore that with all of you. So sorry for stopping you, but I want to explore that idea with all of you. First idea, the mean between the 2 main peaks. Okay, I will do that for you. Look, the mean between the 2 main peaks is here, because you have 1 peak here and 1 peak here. Sorry, guys. But the mean between the 2 main peaks is here. Okay, bad luck. Huh? It's not your fault. It's but it might be a little bit unstable. That's the message. But you're right, still. In most of the cases when you have 2 populations of pixels, the mean between the peaks is not a bad idea. But the mean between the peaks, as we will see now, is just a particular case of the optimal threshold. Now I want to explore the idea of your colleague here. we have noise in the image. For sure, we have noise, more or less depending on the acquisition. What would be the histogram without noise? What would be the histogram if the image would be crystal clean?
2 peaks.
2 peaks. 1 peak here, amplitude being the number of black pixels. 1 peak here, amplitude being number of white pixels. Sharp peaks. Why isn't it the case? Well, because we have noise. I will not play that with you long. We have noise, so it means some of the pixels that should be dark are actually not that dark. And those pixels that should be bright are actually not that bright. More noise will generate a broader, I will say the term, a broader distribution. More noise will generate a broader distribution around the mean of the objects or the background. So does this give you an idea for what would be the best threshold? We come to statistical analysis here of distributions. And now I would like to use the board to do that with you. And what we will do now is to define the best threshold. Should do something like that. In statistical terms. Because at the end of the day, the definition of this threshold, which looks like, you know, stupid, it's one value in a grayscale image, can be defined extremely correctly in a statistical sense. When we define a threshold, we do classification. Okay, we are in chapter 1, not in chapter 3, but still we do classification, because if I define a threshold, I do a classification of my pixel. Either they are below or above the threshold. So this is a classifier. Simple, but a classifier. And so we can say, what is the value of that threshold that will minimize the error of classification? And what is the error of classification? This is the probability. What I want to estimate is that you give me a gray level, here or here, and I want to decide what is the probability that it will belong to class 1 or class, let's say class 1 and class 0. The foreground, let's say, is class 1, and the background is class 0. Okay? So what I want to estimate is what is the probability of my pixel to belong to class 1, knowing its gray value. And I want to estimate, and this is a capital P, it's a probability of the pixel to belong to class 2, knowing its value. And so, if I find the right threshold, it will be easy. If I am on one side of the threshold, the probability of being in class 1 should be higher than that one. If my gray level is here, somewhere above the optimal threshold, this probability should be bigger than that one. So I want to find, basically, the value which tells me what is the separation between the regions where the probability of belonging to class 1 is higher than that one, and the opposite. Okay? So basically now, I want to find this threshold, which is what is the value of the gray level which makes those two probabilities equal. And I will do it first mathematically and then graphically. Now, what can we say about the shape of those curves? They are Gaussian in which case? Why do you say Gaussian?
They look kind of bell-shaped.
They have bell shape that looks like obvious. But you are kind of right saying, I mean, intuitively we say Gaussian. First because we know it and it's simple. Well, but that's not the reason. We discussed that last week. Why can you reasonably assume that those two shapes are actually sampled and approximated versions of Gaussians?
The noise is Gaussian?
Yeah, we can do the assumption, or we can have good reasons to think that the noise is Gaussian. And indeed, in a camera with low exposure, the noise is pretty nicely Gaussian. Not completely, because you have no negative pixels in a Gaussian distribution, you should have negative values. But okay, let's say reasonably we have Gaussian noise. Whether it's white or not, we don't care, remember. Huh? It's Gaussian that matters here. And so if we have those two distributions that are nice, two nice Gaussians, then we can probably play with this. What can we say? When you see that, what is the name of the guy that comes to your mind? Base, obviously, right? This is the conditional probabilities, so you will use the Bayes rule. And you all remember the Bayes rule, right? So basically, this is the probability, the distributions of x knowing y1 times the probability of y1 divided by the distributions of x, whether it's equal to the probability of x knowing the W2 times the probability of W2 divided by the distributions of x. You open your books of statistics and you can write that. Now, the question is not to write it, it's to understand it. So, what we want to find is what is the gray value that equalizes those two probabilities, knowing that when we have them, we will also be able to say which region corresponds to a probability of belonging to 1 higher than 2 or 2 higher than 1. And so the threshold, the one that separates those two regions of the range, is the one that equalizes those two probabilities. Okay? So now, I have that, I can write that. Okay, that's one page, one formula. Now, what does it mean? Okay, they are distributions, so basically we will not care about the denominator. We will basically say we want to find the value of x, which is the threshold, such that p of x times W1 times, knowing W1 times probability of W1 equal p of x, knowing W2 times p of W2. And if I can find a color clay, yes I can. I will. That's the only thing I will write on the board. I want to find now what is the value of x that equalize those two quantities. And we want to understand them now. So obviously, what do you recognize there? Can you recognize something? If I read that in my poor English, this is the distributions of the gray values for the pixels that belong to class 1. This is the distribution of the pixel knowing that the pixel belong to class 2. I said knowing here, I could say the same there, okay? So, that's okay, you know? Does it look like something we know, or we see, or we can see? Distributions of the pixel of class 1, distribution of the pixel of class 2. Do you see them somewhere? Sorry? We say Gaussian. That's exactly what we will assume to be a Gaussian. Exactly. And do you see them on the histogram? Kind of. This term has a shape which is that one. The Gaussian here is basically that term. The Gaussian here is basically that term. So now if I, how can I do that? If I redraw the same histogram, I want to stay on this side because of the camera, I'm sorry. Okay, not that good, but anyway. So I will redraw the histogram and you will recognize something I will do. This is an exaggerated version of the same histogram. Well, not quite. The histogram that I see is actually this. Huh? So in green here you have the histogram. And what I say is that in this formula, which is somewhere here, the distribution term here is pretty much like this green part. I say proportional to. And this one here is nicely proportional to x knowing W2. What about that term? What about that and that? What is this? In statistical terms, what is this probability? Do you recognize it somehow?
That's the probability of a pixel to belong to the foreground or the background.
Yes.
So
Not knowing anything about his appearance, what is the prior probability for the pixel to belong to the background or the foreground. And by the way, I mixed up my 0 and 1s become 1 and 2 here, okay? Doesn't matter. This is the prior. What does it mean? Again, look at the histogram. Where do you see the prior? Can you say something about the prior? If there was no noise, what would be the probability of a pixel to belong to class 1 or class 2 if you had the histogram of the sharp, noiseless image? Yes, but again, if there is no noise, there are two peaks. The height. The height of the peaks, the number of pixels, are a good estimate of the probability. This probability could be nicely estimated, and you're right actually, with the surface under the curve, but I make it simpler. If I had an histogram with two peaks, the probability of belonging to one can be estimated, it's an estimation of course, by the height of the peak divided by the number of pixels. This is the ratio, and the same here. Even now we have noise, so basically we don't have peaks, we have Gaussian distributions, and indeed the prior can be estimated by the surface under the curve. So now I will correct what I drew here. What I drew is not totally right. This curve is actually not proportional to the distribution, but proportional to what actually? The distributions times the prior. Because this curve has a height. This would be true if the two Gaussians would be normalized to 1, because then it would be proportional to the distribution. The distribution has to have an area of 1, an integral of 1. But this curve is obviously lower than that one. The surface is not the same under the curves. So obviously what those two curves are is that they are proportional to that times the prior. And the same here, times the prior. I want to stop just here 1 minute. Is that clear? It looks, again, what we are trying to do is find a stupid threshold on this stupid pixel histogram of this stupid image. But still we are doing something that you might like a little bit. Okay? Is that clear? Do you agree that if I'm able to fit, to recognize two Gaussians there, they identify those two quantities? Yes? Why do we have? Yes. So, we kind of agree that the shape of those two bells correspond to the distribution of the noise. Basically, the variance of those Gaussians are given by the variance of the noise, the power of the noise. Well, the variance, yes, the power of the noise. But the height of those two curves, obviously, are not equal. And if they are distributions, they should both be Gaussians. So even if they have not the same variance, they should have something that makes that the integral remains 1. Because a distribution of probability has an integral from -infinity to infinity equal to 1. Yes? So basically, it's true that the shape has something to do with the distribution. But the amplitude of those two bell shapes is actually governed by the prior. And that's what you said. The area under the curve here is actually not 1, but that, proportional to. It's actually number of pixels, so I should add times n here to put an equal sign. But the n is the same on both sides, so the proportion remains correct. So basically, that's exactly what you said. We have a distribution with an integral equal to 1 times the probability, which makes this integral proportional to the number of pixels, or to the prior. Is that clear now? Because if we are clear with that, the rest is simple. What do we want to find? We want to find the value of x that equalizes those two probabilities. Those two probabilities, which are proportional to those two probabilities. So basically now, if I am here, and I will get my red clay again, if I can. Yes. And I will try to do that. if I try to look at my pixels, and I take a pixel here, okay, here. This pixel is here in my histogram. So basically, in my histogram, this pixel is here. Obviously here, that curve is bigger than that curve. So for that gray level, the probability of belonging to class 2 is much higher than belonging to class 1. So I will obviously classify it in class 2. Same for pixel black. And so, sorry for asking you a trivial question. What is the value of the threshold? The one that equalizes those two probabilities. Obviously, you will all tell me the right answer. This is the value. The threshold here, t, this is a t, okay? Where the two curves intersect. So now we have found a principled way to define the optimal threshold, the one that classifies those two sets of pixels in the optimal way, by taking the histogram, fitting two curves that have the shape of my assumption on the noise. To make it simple, fitting two Gaussians. That could be in a least square sense, that could be in whatever you want. You fit the two Gaussians with their height, and you find the intersection, and it gives you the right threshold. Why is it the right threshold? Because it minimizes the probability of classifying a pixel in the wrong class. Where do you see this probability of error? Do you see it somewhere? You want a break?
The intersection,
yes? The intersection is here. So what do you mean?
the portion of the area where...
The area under this intersection. Well, to make it simple, this area. This area is the number of pixels. Remember, this is an histogram, so an area is a number of pixels. Huh? This is the number of pixels that with that method will be wrongly classified, because if I have a pixel here that is actually really coming from this region, this distribution, but which has a very dark value because of the noise of my, say, what is it, background. Never know if it's foreground and background. Of that region. Normally, it comes from region 2, but with my threshold being here, it will be classified in region 1. So this will be an error. And all the pixels that have this gray value and that come from this distribution will be wrongly classified. All the pixels that come from this distribution with those gray value will be wrongly classified. But still, you can try to change the threshold, and you will see that the area under the curve will grow. This is the point where the area under those two curves is the lowest. So the classification, the segmentation by thresholding, in that example, will commit a certain number of mistakes, but that's the best you can do. If the two histograms were very nicely separated, the two distributions, those areas might be really negligible, and you might have a perfect segmentation like in this case. Okay? Questions or comments? So then the rest of the slides just express that, but that becomes simple. You have all the ideas that you proposed. Oh, we have to come to the ideas that you proposed. And you have my optimal thresholding. And if you look at different histograms with their fitting, you will recognize that choosing the minimum between the peaks might be very close to the optimal one, or not. Here is the optimal, which is the intersection. It's not the minimum between the two peaks. And here in this histogram, which is still a bimodal histogram, there is no minimum between the two peaks, still you can find optimal threshold. Okay, it will be very bad because the two histograms overlap a lot, but still you can find it, and that's the best you can do with one single threshold. Okay? So how do we fit that? Well, that's a good question. You can say distribution 1 is a Gaussian, distribution 2 is a Gaussian. A Gaussian has parameters, amplitude, mean, and standard deviation. And you can use different methods to fit that. You can find the best value of those coefficients that minimize the difference between your histogram and its fitted value. And you do your preferred optimization algorithm to find the best values of the two histograms that fit the two curves that fit the histogram. And there is a very famous method called expectation maximization that does that, but you can use others. That's a detail. Now just one last comment. What time is it? Yeah, it's time. It will be time to break. Just one last comment. One of you or several of you had the idea of finding the mean between the two peaks. Just think for 1 second. This is an extremely good idea, and this is optimal in some cases. In which cases, finding the mean between the two peaks is actually the optimal threshold.
Both priors are equal and the Gaussian shape is the same.
Exactly. So you see, simple, intuitive IDs can be optimal. You can define the best classifier in the world with simple IDs only under some assumptions. And this is something that we will see again when we talk about classification and Bayesian classification. You will see that very simple classifiers can be the best solution in the world in some cases. So keep that in mind. I will break now, but my summary for this first hour is that we can spend half an hour on finding a stupid threshold, which is okay. Okay, questions, comments? If it's not the case, let's do a first break and we meet in 10 to 15 minutes. Okay, thank you. What I will do now is to go quickly to very simple things that you have to do when you have this tool. So what we have seen is basically you can define either in a very simplistic and intuitive way or in a more principled way, you can define the threshold. And it's very powerful, surprisingly powerful. When you have that, you can do a lot of things. You can, for instance, decide to segment images. There is an extension of that you can do. This is an image of a brain, as I already seen in the introduction. And doing thresholding would be a way to extract in that image what is called the white matter and what is called the gray matter, for instance. Now you might, in some cases, work with pair of images. Those two images represent the same individual, same location in the brain, but two different modalities. We say this is a T1 weighted MRI, this is a T2 weighted MRI, whatever it means. But you have, for each pixel of the brain, two values, that one and that one. They give complementary information. So we can actually draw a 2D histogram. What is, for a given pixel, the value of image 1 and the value in image 2? And a given pixel will give me a point in this 2D histogram. And here doing thresholding is a bit more complicated. You might, if you do thresholding on both axes, on both images, you will basically define regions that are defined by horizontal and vertical lines, a threshold on the first value, a threshold on the second value, and you cross the fingers that it will isolate different regions, and it might work. This is, again, a simple classification, but this case in 2D. What we will see in the lecture of classification, which is what we want to do in machine learning, basically, is how to draw classifiers that do not do just thresholding, that do a little bit more than that define the optimal intersections between the regions in the feature space. This is the feature space. I have two features, gray level in image 1, gray level in image 2. I have a feature space, and I want to basically define regions in that feature space. This is the basics of classification. This is not this lecture, though. Okay, now when we have that, that's very nice. It's simple, it works. It allows you to separate what is the foreground and the background. But still, it doesn't tell you what are the objects individually. It doesn't separate the objects. What we have to do really is to consider the region more than the gray level. And what we will see now is very simple. It's called region growing. Basically, when you have a pixel, you know that now with the threshold, you know that whether it belongs to the foreground or the background. But you don't know whether it belongs to a given object A or a given object B. So basically, what we will say is, okay, a region, an object, is actually all the connected pixels that are in the foreground. That's a natural way to define an object. All the pixels that are connected to each other and are in the foreground create one object. And another object will be another set of connected, disconnected to the first one, but connected together, which are in the foreground or which are above or below the threshold. Okay? So this is really region growing. I have a point, I easily know whether it's part of the foreground or background. And from that point, which I will call a seed, I will basically grow a region by including all the neighbors and the neighbors of the neighbors and the neighbors of the neighbors of the neighbors that are connected to them, because they are neighbors, and that are also in the foreground. This is region growing. So I need a criterion. It's my threshold. I am in the foreground, but it can be another criterion. It's not necessarily only a threshold. Any homogeneity criterion, I have a pixel in the foreground. My neighbor, is it in the foreground or not? I need a criterion. In my example, the threshold is the criterion. And then I search iteratively all the neighbors. And all the neighbors of the neighbors and all the neighbors of the neighbors. And doing that, in computer science, you know it, in programming, it has a name. Doing something that do a certain action on its neighbors and then repeat the same action on the neighbors of the neighbors and the neighbors of the neighbors. This has a name. This is recursive procedure. It calls itself. And if you have already implemented a recursive procedure, it's simple because it's 2 lines, an action, and the call of the same procedure, right? And that's exactly what you can do. You can, in 2 lines, let's say 3, program a recursive procedure that will, from a seed point, include all the pixels that share the same homogeneity criterion, that are below the threshold, say, or above, and are neighbors. You basically explore the 8 neighbors of a pixel. If they are in the foreground as well, you say, they are in my object, and I relaunch my procedure on them. And the procedure is to look at the neighbors again. Of course, you have to make sure that you don't play ping pong, because a neighbor of a neighbor is, my pixel is also the neighbor of the neighbor. So you have to say, I go there, I mark them as already visited, because I don't want to come back, and then I apply, because otherwise you will come back to the previous one, and that will not work. But except that, it's really 3 lines. Or including that, it's really 3 lines. And it really works. You say, this point belongs to my object, boom, you get it. And then you can do very nice segmentation. It's heavily used, for instance, in medicine. In medicine, you might want to say, what is the size of this tumor? Probably the doctors easily see that this is a tumor. You don't need a computer to say this is a tumor. They see it, that's it. But if they just click in the middle, they want to say what is the extent of that lesion and how it evolves through time, for instance. And with a 3-line code, you very nicely segment that. I have a threshold to define what is the tumor and what is not. But the threshold alone is not enough because there are pixels here that have the same gray level. But if I click here, boom, it will find in 1 fraction of a millisecond all the pixels that are connected and are above the threshold. And you can segment a tumor, you can segment the head like that, you can segment a lot of things by that. It requires a little bit of interactivity, which is just clicking somewhere, which is not an issue for some applications. A good interaction, simple, is probably sometimes better than a bad automated system. Plenty of applications. Now, imagine you have this tool. Now, you manage to find in MATLAB, in Python, or you programmed yourself, a region growing methods. A region growing method is a black box that you have now, which has as an input the pixel coordinates. And what it does is that you give the pixels the coordinates of the seed, and it gives you the object. Okay? Now, I want you to use that black box again. The black box is, I give the pixels, the coordinates of a pixel, and it gives me all the connected components that are on the same side of the threshold. Can you use that to count the number of objects? I want you now to write, or to imagine at least, a method, an algorithm, that will count the number of objects. Think for 1 minute. No, less than that. Think for 10 seconds. The tool that you have is this region growing box that you found and that is programmed. Can you give me an algorithm that will automatically count, which means label, and give a label, give a number, to each of those objects? The definition of an object being the connected components with black value. Who wants to start? Who has an idea? A routine that will be systematic, no interaction, and I will label all the pixels. Sorry, he was first. Sorry, guys.
Start at pixel 0.
You start there. I agree.
Go sideways.
What do you do first? You go sideways?
If it's above the threshold or below the threshold.
Exact. So you check. So obviously it's above. So what do you do?
So move on.
Okay. You don't want to label the background?
No.
No? Okay, fine.
I don't know. Maybe we can.
Yeah, okay, fine.
Keep going until you reach something that's below the
Hop, here.
threshold.
That's my first one.
You put this into the algorithm.
Okay, I start, this is my seed. This is object number 1.
Okay, label that.
Yes?
Now that we've identified the object, label it so that we don't...
That's done. That's done, okay.
Yeah.
What's next?
Keep moving on past the object. So we see that this one has a label. Don't send it into the black box again because we've just...
Okay, here.
Now we keep moving.
Why?
Sorry?
I'm here now.
Yeah. So
Okay, I'm above threshold. So I keep moving, right?
Exactly.
Until I reach another non-labeled. Okay, I will not do it for all the pixels, okay? I get to the second one, I label it with number 2, and I keep going, okay? That's how it is. This is called labeling. So again, extremely easy to program. This is called BW label in MATLAB, so you don't need to program. But okay, and in Python, I don't know. But it certainly exists. And you will get it. You will really get it, and you will get all the pixels. This is labeling, and this is extremely important. Because, for instance, now, you want to extract out of this pixel, so you have the original image, which is the noisy image. And the task now for you is to extract the biggest object. This is the task I assigned to you. The most important one is the biggest. Well, now you know how to do it. You have to define the optimal threshold, and then you have to use it in the region growing and labeling process to label all the black pixels. Black means below the threshold. And then you get a label, and you can count how many pixels you have with label, I don't know what it is, 5. And if this object has the highest number of pixels, this is the biggest one, and you are done with your task. It's not very complicated, but you will have to do that. For instance, the first lab you will have to do will basically be to extract the brain in an MR image out of the skull. And luckily enough, the brain is the biggest object in that image. So I don't want to tell you what to do, but might be a good idea. Here segmenting, again, a lesion. This is not a tumor. This is a stroke, an accident vasculaire cérébral in French. And again, by clicking in one point, you get the stroke very easily. And this is a diagnostic tool that you can build. OK, there are now a range of methods that I will not see. You read the description in the slides. They are crystal clear, that you can use to play with these basic blocks. So you have a way to define regions. Now, to do a proper segmentation, you might sometimes want to define the different regions by labeling, and then to fuse them, to merge them by a certain criterion of resemblance. And basically, this is region merging. I will speed up a little bit, because I spent an hour on the thresholds. If I do that for all the methods, we're not done yet. So region merging is a way to put together regions that we identify with a simple methods that will probably do a little bit of over-segmentation. Splitting is the opposite. You basically say, I start from my image and I divide it, and that will end up with something that is my segmentation. I let you read that. It's very simple. And split and merge is the combination of both. You will find those 3 types of methods heavily in the literature. They are simple, and my understanding is that with what I explained today, which is not that difficult, I would say, you have the basics to understand them. If you need them one day. I don't want to spend your time in seeing things that you can easily read. Okay? Very good. So we are done with the regions method. Just remember, 2 families, regions or contours. We are done with the regions. There are many more things that you want to do with regions. But this is the basics. Let's move to the second part of this course, which is the contour detection, edge detection. I will alternatively use contour and edge. If you don't look at your slide or on my slide, what is a contour? Someone at the back said it's a sharp transition. The term frequency was used. It was not the best idea. But it's a sharp transition indeed in terms of spatial frequency. It's an area of high frequency. But that's not the main definition. The definition that I want to use today is it's a part of the image where you have a sharp transition between one gray level and another. Okay? And so obviously, if we want to do contour detection, we want to find all the points that really are located on pixels of sharp transition between one region and another. And you don't have so many possibilities. I will just use the board once more. And there is only one thing to remember, only one, which is composed of 2 parts, but okay. I want to find I look at the image, and I look at the profile of the gray levels, how it evolves. And I will do that in 1D because it's simpler. So along a given direction in my image, whatever it is, vertical, horizontal, or any other, what is the gray level? And I somehow, if I look at the gray level on the image that you have in front of you, this is black, and then it becomes white. So what you have in front of you looks very much like that in terms of gray levels. And obviously, the edge that I want to detect is here. So obviously, the edge that I want to detect is here. So that point of my image would be recognized as an edge. Now, give me ideas how to detect that point. I need 2 IDs and 2 IDs only. Yes, 1 and 2.
So we can take the maximum of the gradient.
Yes, or? Continue. Or? Either you take the maximum of the first derivative or? Zero crossing of? Sorry. So if I estimate or calculate the first derivative of this profile, I'll get something like that. And if I calculate, and it was a very bad idea to put it there, the second derivative of the profile means the first derivative of that profile, I'll get something like that. And at that location, which is the inflection point here, I have a maximum, as you can see, it's right there. And it's right there that I have a 0 of my second derivative. And this is the only thing you have to really remember from edge detection. All the existing methods, absolutely all the existing methods for edge detection, try to estimate, one way or another, points that are located at the maximum of the first derivative or at the zero crossing of the second derivative. Nothing else in the world. Yes?
I don't understand what are the axes?
The axes are just an axis in an image. It's difficult for me to show you the gray levels in 2D. You remember, if I have a 2D image, the gray levels are a surface. But it's not that easy to draw on the board. So I just draw one line of that image. So this is basically, this axis could be, for instance, if you consider the picture you have in front of you, is this axis. And I move and I see black, 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 shrink, white, 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 white. This is exactly what I see. Black, 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 shrink, white, white, white. And my edge, which is here, is that point, along that line. But of course, it's everywhere in the image. There are edges. And so, some algorithms use the estimation of the first derivative and find the maximum. Some algorithms use the zero crossing of the second. Yes, please.
You say that it was 2 ideas, but this is actually the same.
Of course, it's the same, but you have two methods that you find in the literature. Those that try to do that, those that try to do that. That's just what I mean. But it's the same idea, of course. It's the same principle. It happens that finding the zero crossing of the second is easier because you have to find values in the estimation of the second derivative that are tiny small.
Is there some algorithms that are just like better exploit the information?
Sure.
What is the situation?
That's my next slide, if you don't mind. I'm not done with the edge detection, you know. I still have half an hour to talk. So, either or. Historically, people have tried that. But in practice, those ones are easier and more robust. You will see why. I now want to browse a little bit the history. You might consider that, how can I say, funny or trivial or whatever. Remember that you're young guys, but computers are also very young. So the methods that you will see have been designed probably a little bit before you were born, but not that much, at a time where computers were extremely slow, low memory, and expensive. So those methods are certainly not the best one in the world, but you want to do image processing, recognition in real time in an industry 30 years ago, only 30 years. 30 years is not that much, huh? What I will show you is what you could do at that time. Now we can do much better. We can do machine learning. But at that time, what people were doing, so what I have here is exactly that. Huh? You have an edge. This is maximum or second derivative. What people have proposed when they they started to investigate the digital image processing 30, 40 years ago, is filters like that. Because at that time, having a processor that in real time on TV at 25 frames per second, which were not digital, so you had to digitalize them somehow, have a digital camera at that time was just crazy, and doing a real-time processing was crazily complicated because of the memory. And so what they proposed is this. What do you have there? You have a filter that takes an image and calculates extremely simple operators. But you recognize there the finite difference approximation of the first derivative along that direction and along that direction. You have to add a 4-byte memory, which at that time, you know, you cannot realize that probably, but go to the Bolo Museum and you will see. That's what people were doing. They were calculating that, and all the values that were a little bit big, we have to find the maximum of the first derivative. They were a little bit big, okay, it is an edge. I would not do that now. Then more sophisticated approximation of the first derivative were proposed, and the two key names that you will recognize very frequently in the literature are Prewitt and Sobel. These are the masks that you recognize also being approximation of the first derivative. They basically calculate the difference between a point and its neighbors. So this is the finite difference approximation of the first derivative, obviously. And you have different masks for estimating the derivative in different orientations, Prewitt and Sobel. You recognize that surprisingly the masks are becoming bigger. Not because they had more memory, but why do you think that those masks do a better, I have to explain what better means, but a better approximation of the first derivative, better estimation of the first derivative. Why do you think it's better like that? Let's be very practical. Do you prefer that one or the previous one in doing an edge detection?
Because of noise.
Yeah. This one will do an estimation of the first derivative, calculating it over more pixels. If they are affected by noise, this will kind of cancel out, be cancelled out. The more you take, the more you cancel, and you do actually what you want. If I do that, any single pixel which is noisy will create an edge, because there will be a difference between a pixel and its neighbor if the other pixel is noisy. So this is absolutely not robust. Oh, sorry for Robert, but that's life. So these ones are extremely simple. Today, you still find edge detection method that run in real time doing that because it's extremely simple. But it works. It works very nicely. But this is kind of historical, what I say here. There is one that is heavily used still today, and that I like very much. There is one that I like very much. There is one that I like very much. Generally, people, you know, raise up. I like it very much. Yes. You get my effect. Come on. These are two approximations of the first derivative. Here, you assume that basically the pixel, you ignore the fact that this pixel is at a distance square root of 2 as compared to that one. So you have the same weight for the estimation of your first derivative. This is probably a better approximation because you say this one is closer than that one. So to estimate the first derivative, you weight more the one that is closer than that one. So this is a kind of a integer. We work with integer at that time. Having digits on 8 bits was already very good. So you work with integer estimation of the first derivative, this one being a kind of a better estimation of the first derivative as compared to that one. These are evolutions. Well, these are rotations. If you take that one, this is basically the estimation vertical, and then there were approximation to estimate the rotated version. This is 45 degrees, this is 90 degrees, and so on. These are rough approximations. Huh? Put that in the historical context. Huh? But let's come to the one I like. The zero crossing of the second derivative first is a good idea, because if you have a robust estimation of the second derivative, finding the zeros is easier than finding the maximum, which is always difficult in a 2D image to find a local maximum, because you know, I have to look around and you might be in strange configurations. And the most popular and the most robust and really the fantastic method that has been proposed by David Marr. And David Marr is actually a superstar. If you're engineers, but if you have friends in psychology, they know David Marr as well. Because this guy investigated the visual perception of humans, both on the psycho side and on the processing side. How do we perceive the world? And this guy is really a superstar, David Marr. And he proposed this very interesting method, which is called Marr and Hildreth, the other guy working with him. And the actual name is the method Laplacian of Gaussian. There are two complicated terms there, Laplacian of Gaussian. And the key idea is this one. You have an image, and you want to calculate the zero crossing of the second derivative. Okay, Laplacian is the operator for the second derivative, and this is the Laplacian. And obviously, you want to calculate the Laplacian of your image. And every point that will have a zero value after calculating the second derivative will be your contours. Fine. But what those guys coming from the visual perception community said is that, yes, but probably I'm not interested in all the points that have a zero crossing. I'm probably not interested in all the points that have a transition in that image. What do you want? You are looking at the screen, the picture that you have in front of you. And if you look at the contours, you might be interested in reading the letters. You might be interested in finding my profile. But I'm not sure you're interested in finding the contours of those little dots that are on the screen and these things that I put it there. There are different levels of things that you are interested in. And what this method proposes is to say, let's decide. Let's filter out the details that I'm not interested in before calculating the second derivative. Let's apply a very simple Gaussian smoothing with a parameter, sigma. And you set this parameter, you as the user. And depending on the value of this parameter, you will have a broad or a narrow filter which will smooth completely your image or not. You see? Having a narrow filter that you will apply on your image will basically calculate for each pixel the average of only its neighbors. A narrow filter, a narrow impulse response, will basically average for each pixel just its neighbors. If it's really tiny narrow, it will not do anything. And the bigger the sigma, the bigger the smoothing. Yes? So you have a parameter there. You choose which contours you want to keep. Because if you take the picture you have in front of you and you filter it by a Gaussian of that size, I don't know what it is, but that size. What will probably happen is that since I'm very contrasted on the background, my contours will remain. They will become a little bit more like, not sharp, a little bit more smooth, but my contours with the background will remain. Yes, I'm dark. But probably this will disappear already. It will become completely fuzzy. And those little things here will be smoothed out. And you choose. And after that, you do the second derivative and you get the result. So that's the methodological beauty of that method. You choose. And you can even decide to do a continuum of detection. You set different values, even a continuum values for that, and you get different edge maps. Okay, this is called the fingerprint of an image. Now, this is beauty number one. You choose your resolution of analysis, which corresponds to the perception we have. I don't care really of the texture of your shirt or your pullover. I care about your contours. I don't care whether you have a shirt of a given shape or another. I don't care that I filter out that when I analyze what I have in front of me. Or not, if I decide to focus on you. Yes? Okay, what is a Gaussian filter? It's a filter. In 2D, it's a square, a box, where the impulse response has a Gaussian shape. So it's a n by n matrix with the center, and the values of this filter are big in the middle and decrease when you go to the side. Okay? So it's like, if you look at the filter, it looks like Gaussian. Okay? And what does it do? Well, a filter is something you convolve with your image, right? So you take it and you place it everywhere on your image. And the convolution, the operation of filtering is doing a convolution. You agree with me, yeah? I guess you had signal processing with me or not? Oh, so you should know it. So you take this filter and you convolve it on your image. And convolving means that for each pixel, you replace the value of the original by the weighted sum of the pixels and its neighbor weighted by the value of the filter. Correct? So basically, you replace the value of the pixel by the pixel plus a large part of its close neighbors, a little bit less of its neighbors a little bit further away, and so on, and at the end, almost nothing. And if your Gaussian is extremely broad, you will basically average with similar weights pixel on a wide range. So it basically blurs everything. This little edge will be basically replaced by the mean of a big circle here. That means it will disappear. It will become white, obviously. While if you take a narrow Gaussian, this will be replaced by the weight of the average of its neighbors around, the 4 or 5 pixels around. It will remain there. So playing with the sigma gives you the blurring of your image before calculating the edge detection. This is beauty number 1. Beauty number 2 is here. You can show that what you want to do, beauty number 1 is this. I want to calculate the convolution of my image with a Gaussian. Again, my 2 stars is my dirty notation for convolutions in 2D. What I want to do is taking the image, blurring it with a Gaussian that I decide, and calculating the Laplacian. And the beauty number 2 of that filter is that this is actually equal to convolving my image with the Laplacian of the Gaussian. Laplacian of the Gaussian. The Gaussian is here, the Laplacian is here. And why is it a beauty? Because calculating the Laplacian of a Gaussian is analytical. The Laplacian, the second derivative of a Gaussian is this. Believe me. You take a Gaussian, you calculate the second derivative, and you get what is called the Mexican hat. That's the name, sorry. And again, the width is given by the sigma. But you have a closed form, an expression for the second derivative. You don't have to approximate the second derivative. You know what it is because the second derivative is the second derivative of something that has a closed form. While if you were doing this, you would have to do a very nice approximation, discrete approximation of the image. Very much like what we do for the first derivative. I'm coming, but I'm finishing. For the first derivative, we had more or less sophisticated approximations by Prewitt, Robert, Sobel, and so on. If we would like to use that, we would have to have a discrete approximation of the second derivative. Here we don't. Just a moment. Here we don't need that. We can have a closed form expression for the operator, so we can calculate the n by n filter that we have to convolve my image with. Without doing approximation, we just sample the actual second derivative of the Gaussian, and we convolve my image with that, and it will immediately give me an image where the zeros will be my contours. I let you digest that, and I take the questions. Yes?
The F represents
the image.
The image. But where is the second derivative of the image?
There. That is the second derivative.
Yes, but in the second part, you
Well, it happens that the convolution and the second derivative can permute. And so basically this, by mathematics, is equal to the second derivative of the Gaussian, which has a closed form. So I can calculate the second derivative of the Gaussian. So the beauty is this. Two beauties. One, the idea of filtering that you get, okay? Second, if I want to implement that, I would have to filter my image and then estimate the second derivative of the image, very much like what I did for the first derivative. And as you have seen, this is sensitive to noise. There are approximations of the discrete versions of the first derivative, and you would have to apply it twice, so it's even less stable. Here it's much simpler. You know that you want to convolve by a Gaussian, and that mathematically, calculating the second derivative after convolution is equal to calculating the second derivative of the Gaussian itself, and then convolving the result with my image. And that I can have much better approximations of this second derivative because it's the second derivative of an exponential. I mean, I know the expressions. I have to do the Laplacian of that and sample that, and that will create a filter that I will convolve with my image, and the result will be something where at each of the zeros that will be my contours, or the contours will be at each of the zeros. Let me show you an example and then I take your question. This is an image, and I decide to convolve it by this filter, in 2D of course, with different sigma, so different width. And after that, I mark in white all the points that have a zero value or a very small value. And you see that playing with my sigma, I can get all the noise, or less noise, or only the main edges. That's what you see. Now I take your question.
So this is actually a continuous
Yes.
rotation. But in order to make it for a real image,
You sample.
we need to sample, for example, 8 samples if we want to see only.
Well, you would do more, probably.
Yeah.
Because actually, what you have to do is to say, OK, I set my sigma, which is basically my resolution that I want to do. When I've done that, I look at what is the shape, in continuous terms, of this Mexican hat for that sigma. And obviously, then you will decide the size of your filter, digital filter, to be in that range. And then you put the values sampled on that, and you will have a very nice digital version of this filter. But you will set the size of your filter such that you have a very good approximation of your second derivative of the Gaussian.
What I'm asking is actually, is there a prior that we can know on the sample frequency of this thing based on the frequency of the image?
No, you have to sample the filter, not the image. So basically, you have to make sure that the digital version of your filter corresponds to the continuous. So here there is no Shannon's theorem or something like that. The point more is you have to decide the sigma. And this is related to the content of the image, because this sigma is related to the details that you will basically discard or keep. OK? Clear? Clear? I like it very much. And you get big details or small details or big details, depending on the sigma. Sorry for the quality of the images. OK? What time is it? I need another 15 minutes, and then I will be done. Do you want a break, or we continue and you finish and you have lunch before, or you do what you want before? Break or not? We continue? Everybody agrees we continue? 15 to 20 minutes? We'll see. OK, good. Last part of this course. We are done already with the regions-based methods and the contour-based methods already. What we will see in the next lecture is to show you the opposite of the spectrum. These are the basics of the basics, but it works. What we will see in the next lecture, so not next week, but next lecture in 3 weeks, is a very advanced method called active contours with heavy advanced mathematics to do very robust, coherent, blah, 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 segmentation. But what you will see there is that even this very advanced method relies on things that we have seen today. Seeing this will not solve all your problems, but will allow you to understand all the existing segmentation methods, including the most sophisticated ones that could be the active contours. That's my point. And I will prove that in the next lecture. In the meanwhile, I want to finish with a separate chapter. And you might have already seen that in some of your cases. In that case, I apologize, but I think it's good to see it here as well. We are done with the basics of the segmentation. So we are basically done with taking an image and getting its nice, clean segmentation like this one, and we know we can label and blah, blah. But in case there is more noise, my optimal segmentation might be that, or that, whoops, or that. Depending on the noise, my optimal threshold, which is gone now, okay, might lead to that. Still, this is the optimal segmentation in terms of choosing and applying a threshold. This is the best you can do with one single threshold for that image. What I will see now is a series of methods that will allow you to post-process, to clean up that a little bit, which are a little bit, well, which have a complete different philosophy. The theory is called mathematical morphology. Just for my knowledge, who has already studied mathematical morphology? And among them, who is French? Voilà, that's why. This has been invented by Jean Serrat at the École des Mines, and so it's nicely taught in France. But That's a joke, I'm sorry. But it's not a joke, but I mean, it's not a surprise that you studied that in France. But still, it's very nice. So what I will see is a series of operators. Mathematical morphology can be seen in a very practical way, and that's what I will see today, or in an extremely theoretical way, as it was formulated initially. Since we are recorded, I have to be a bit careful of what I say, but hopefully it will not go on Google, on our YouTube, I mean. Mathematical morphology has been invented by Jean Serrat. Jean Serrat, as far as I know, is still alive. I met him a few years ago, but not recently. He used to be a professor at the École des Mines, one of the most famous schools in France. And historically, it's not a surprise that it emerged at the École des Mines. You will see why. And Jean Serrat wrote a series of books to describe mathematical morphology, and he created the whole theory, which is a set theory, and théorie des ensembles, for these operators that apply to a lot of things, not only images. And it's a complete theory with basically which is described as theorem, demonstration, lemma, 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 theorem, demonstration. And you have 2 books of that. That's very nice to read. This is it. And then you have the practical application in images, and people have derived the practical applications and algorithms to implement that and explain that in a simpler way. And the reference is Bob Aralick. Bob is also still alive, hopefully. This paper is the one that you can use. The funny story of that is that when you write a paper where you use mathematical morphology, and we do that a lot, you obviously have to cite that, but I presume that nobody has ever read that book. I never read it. I will cut that in the movie, of course. Good papers. Okay, what is it about? Again, simplified version of it, but practical for image processing. This is a set theory, so we use sets. And I will see the binary morphology. You have slides about non-binary morphology at the end. I will not see them. Binary morphology means we have binary images. We have that. And we want to clean. We have noise that created little spots in my image. Binary, they are black. Or we have noise that created little holes in my image. They are white. Binary. So we are working with that, and our goal is to remove that noise or to fill those holes. Intuitively first, what differentiates those pixels from those pixels? What differentiates those pixels that I don't want to keep to those pixels that I want to keep? Just simple.
The neighboring area they have.
Exactly. If I look around, I will not find so many black pixels. Here I will. What is the difference between those little holes here and the white here? Again, they are surrounded by the object. So that's basically the philosophy of mathematical morphology, to clean isolated stuff, isolated pixels or isolated holes. Now it comes with a whole framework, a very strict and coherent mathematical framework of set theory, and I will simplify it a lot here. This is a binary image, okay? 4 by 4 pixels. And in those pixels, I have an object. And the definition of what I will call an addition in the set is to add a vector to the set. It will be a translation. So it's very simple. So the translation uses the operator of set addition to create an object that is the translated version of my initial object. I have an object here. I translate it by that. I have all the pixels that belong to my plane, which have coordinates, the original plus the vector. Trivial, huh? That's not what I want you to remember. But this is the kind of operators we will use. Now, mathematical morphology is very nice because there are only 4 operators that you have to keep in mind. And you really have to know them. You really have to know them. You really have to know them. 2 and 2. 2 first ones are called dilation and erosion. I take an object, and the whole story of mathematical morphology is to say, as you said, I will process a pixel because its neighbors look different. So the whole idea of mathematical morphology is that you self, as a user, choose a given object. You define a reference object against which you will compare your image. This is very much what you said, that this pixel doesn't look like its neighbors. So you define what you mean by a neighbor by defining an object and you will compare your image to that object. This object has a very nice name. It's a structuring element, un élément structurant, a structuring element. And you define it, and you will see that depending on of its shape, it might give different results in your image. So I have chosen here a simple structuring element 2 by 2. And this is the point of coordinate 0, 0. Two first operations, dilation and erosion. The names speak by themselves. The dilation of an image by structuring element B, the dilation of that binary image by that structuring element means what it means. But since it's very mathematical, you have a nice definition. The dilation of my image by that structuring element is all the points of the image that can be written as the sum of a point of object in image X and the point of object in my structuring element. So basically, this is this point translated by 0, 0, this point translated by 0, 0, this point translated by 0, 0, blah, blah, blah. So I basically copy the same object. Then all those black points translated by 0, 1, and then I put them on top. So I take my object and I move it that way, plus all the translation that way and all the translation that way. And this gives me, at the end, all those points. So the dilation is I take my object and I do the union of all the translations of that object by the point of the structuring element. And obviously, it will blow my object. The bigger the structuring element, the bigger the dilation. If my structuring element is elongated in that direction, it will blow more in that direction. Okay? This is dilation. Union of the translation of X by the values of P. What does it do? Obviously, what does it do? Sorry? Yeah, it closes the holes that are smaller than the structuring element. Ah, that's interesting. So I choose my structuring element such that the dilation will make the holes smaller than that disappear. Yep. So, you see, you choose and you get. Clear? So you basically get rid of the holes, but of course your object is bigger. Opposite, erosion. This is all the points of the plane such that if I take those points, C, and I dilate them by B, I get the original object. So it's all the points of the plane such that when I redilate them, they are in the original image. It's really the dual. So this point belongs to the erosion because if I dilate it by B, I get those 4 points. And those 4 points are in my original image. This point also, because those 4 points belong to the original. But this one not, because those 4 points, there is one that doesn't belong. Okay? So the erosion is a smaller object such that if you redilate it, it's fully included in the original. What does it do? Very much the same as for the dilation. What does it do? Well, yeah. Exactly. It removes everything that is smaller than the structuring element. In my image here, I had a little part here which is a bit strange, narrow. Well, this disappears in the erosion. So if you want to see that from a bigger perspective, if you consider, for instance, this object, dilation of it will give this. By that, huh? Dilation will give this. It will fill all those holes that are smaller than that. And you get a bigger object with all those holes filled. Erosion of that by this will remove all the parts that are smaller than the object. Here you see, you cannot fit the ball here completely in image, so it disappears. Here you can, so it remains. Here the border disappears because the ball doesn't fit here, but it just fits in the middle, so those points remain. So we are almost done, right? With 2 operations, I said there are 4, but with 2 operations, we can almost do what we want. We remove the isolated points, and we fill the holes. Yes, but what?
How do we define the B?
Oh, B. How do we define B? It depends what you want. This is the flexibility and the freedom that you have. You choose the B because you know that you want to keep some objects and remove some other objects. You want to remove the small ones. What do you mean by small? You give an example. This is the minimum size I want to keep. Okay, this is your structuring element. But what is the issue with those 2 operators? They do the job, but
They enlarge or restrict.
yeah, of course, they change the shape. They enlarge and they erode. They are called dilation or erosion. Naturally, what do you want to do to cope with that? What do you think we could do with that to get something which still does the job, but keeps the object of the initial, more or less the initial shape? Just give an idea.
Try one, then the other.
Yeah, let's dilate it. This one managed to remove those parts that are small. Now, if I redilate them, those parts here will not reappear. Only what is close to the object will get its initial shape. So if I do, okay, there are plenty of properties that I don't see. Wow. That one I will see it, I will come back. Sorry, I was a bit too fast. If I did an erosion, I can do then a dilation. This object that I had before, after erosion, was this. If I redilate, I will get something which is pretty much similar to the original one, but with the holes, sorry, this is here, but with the small parts removed, while the rest has the correct size. See it from on the bigger part, take this object, do the erosion. The erosion will basically do something where those parts disappear. The erosion will give you something here. Those parts will disappear. And you redilate, so you will basically keep only the parts that are bigger than the structuring element. You get that. Very nicely smooth version of your original object. This might be the noisy results of your segmentation. This is a nicely cleaned version of your segmentation. And doing first the erosion and then the dilation is called an opening. And obviously you want to do the opposite as well, a closing. After dilation, you might want to erode. My object has become too big. I dilate it. Nice, it will fill this and it will fill this. But it's becoming too big. I erode it and I get that.
Yeah, but didn't we say that erosion is the dual?
Yeah, well, I want to come to that. Just one second. First, before that, 4 operators. Dilation, erosion, opening, closing. Dilation, everybody remembers what it is. Erosion also. You never remember what is what in opening and closing. So let me give you a trick. There is one that you can easily find, closing. Closing means closing the holes. You close the holes. And to close a hole, you first dilate and then you erode. Obviously, first you fill them and then you get back to the original size. So the one that you can easily remember is that closing is dilation followed by erosion. And of course, the opening is the opposite. So keep it like that, okay? Opening and closing is easy to remember. Dilation and then erosion, and the other is the other. Now, there are properties for both dilation and erosion and opening and closing. And I want to come back to that. Sorry, I was a bit fast. Let's say this one. There is a link between erosion and dilation and erosion, yes. Because obviously they are kind of dual. In which sense? Look at this. This one is the object, this one is the dilated. This one is the object, this one is the eroded. There is a link between both in the sense that consider just the foreground and the background. Here, I dilate the foreground. Very naturally, the background shrinks. If I take more space for the foreground, the background shrinks. Here, I shrink my object, the background takes more space. So actually, what it means is that, under some approximation that I will mention just in a moment, doing a dilation is equal to eroding the background. So if you only have one machine that does erosion, you can still do a dilation if you have the inverse operator, the one that flips the background and the foreground. Mathematically, this is written here. If you define the complement being the background of the foreground of the foreground of the background, if you define the complement as being not the object, and I will come back to that, doing a dilation, an erosion, and looking at the background of the result is equal to doing the dilation of the background. So the background of an erosion is the dilation of the background. The last thing is this little operator there, which is basically to say, this is called the reflection. If I have a structuring element, what I have to use here is basically to flip it around its center. Symmetrical, central symmetry, minus the stuff. Why? Because actually, if the structuring element is not centered, if it's not a circle like that, but imagine that it is elongated stuff, well, obviously, dilating an object in that direction is equivalent to eroding the background in that direction. So you basically have to flip the operators, the structuring element, to have the equivalence. Here. Okay. The rest, you can easily read it. There are tons of properties, and you have 2 books of Jean Serra if you want to know more. But you still have the same duality for dilation, for opening and closing, exactly the same properties. And you have another set of properties like idempotence, means that you don't need to open several times. It's useless. Okay, so in conclusion, you have a series of very nice operators, and that's beauty. There are only 4, dilation, erosion, opening, closing, and that's what you have to remember. And it solves your problem of little holes and little islands in your image. So it's a very good post-processing. Just give you 2 examples, and then I would be done. If I take this one and I open it, well, let's say the closing. If I take this one and I close it, closing means close the holes. So indeed, I close the holes, and it works. And obviously, to answer your question, how do you choose the structuring element? Obviously, you don't want to fill that hole. So you want to take it smaller than that. This is your choice as a designer of the method. And you don't want to fill this hole, and you don't want to fill this hole. Yes, you didn't. That's how it works. So you take a structuring element which is smaller than what you don't want to fill. Opening is the opposite. What do you want to remove? Well, obviously, you want to remove small dots, but not too big. You don't want to erode that. You don't want that with your structuring element after the first erosion, this would disappear because it would never come back. So you want to erode enough not to remove that while still removing those points. So you take a structuring element which is small, just a bit bigger than a pixel, and then you get, after opening, the very nice opened image. And that works fantastically, and I encourage you to use that in the lab in 2 weeks. Yes?
How do we decide if to apply opening or closing?
Depends what you want to post-process. If your segmentation was defined such a way that it seems that you have too many spurious points in your results or edges that are really like shaky, you want to use an opening. If it appears that there are small holes in your results that you want to fill, you have to use a closing, and you might want to use both. It's really, you look at the result and you say, I'm not happy. Yeah?
Is there some application that we want not to use opening and closing, but just dilatation and erosion?
Yes, you might want to decide, for instance, to calculate what is called a distance map, and we'll see it in the next lecture. You have an object and you want to see what is the distance between that object and the next object. Well, then probably what you would do is that you iterate dilations. And when you touch the other, it will give you, the number of iterations will give you the distance. This creates, isosurfaces around your object by dilating. Okay. I will show you an example in 1 minute or so.
And we will measure that by checking how much connected one.
By definition of your structuring element. An example, And this is an illustration also, well, this is something we did with students years ago, but this is a typical example of the origin of the mathematical morphology in the School of Mines. This is concrete, c'est du béton. A picture of concrete. And this is not a joke. I mean, the mathematical morphology was defined initially for granulometry, because obviously you compare objects with given, with a reference object of a given size. This is concrete. This is a picture of a concrete, and there are holes, pores, in the concrete. Those ones have been filled with an orange glue. And so in the picture, the pores, the holes, appear orange. And since you know everything about thresholding, you know that you can easily find an optimal threshold, let's say in the red channel, that will isolate the orange from the background. So you get that. And the question we have now is, can we draw a distribution of the size of those grains? The size, not the number of pixels, the size. How many of them, let's say, how many pixels belong to big holes? How many pixels belong to medium holes? How many pixels belong to very small holes? And to do that, you do mathematical morphology. You basically say, I will remove all the small objects and keep the big ones first. So I will do basically an opening. I don't want to fill the holes. I want to remove the small things. So I first do an opening with a structuring element, say, of something of that size. This opening will remove everything that is smaller than that structuring element and keep the biggest object. So here you have the first part of your answer. You count the pixels and you say they are 21% of my pixels that belong to big objects. And you do the difference between the initial and that, you get that. So the pixels that are not here are here. The pixels that were black here and not there are here. Then you do an opening with a smaller structuring element, a little bit smaller, probably of that size, a bit less than that. What you get is that you get only the objects of medium size. You count how many pixels. Okay, it appears that 10% of my pixels are in those pores. You do the difference, you get that. You open the last time with a small structuring element, you count, and yet you get the rest. And so by counting the number of pixels here, 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 and here, you draw a histogram of the size of your pores, the surface, the area of your pores. This is very, very easy. Another example, okay, there's binary morphology. The non-binary morphology, I let you read that. Another example was in biology, where you had to basically sort what is black and big versus what is black and small. And by doing mathematical morphology, you manage to isolate what is black and big versus what is black and small, and isolate the individual objects. The rest I will not describe here, I'll let you read it. Voila, questions? Mathematical morphology, obviously. So, to get to that, it's okay. You threshold that image on the red channel. So basically, you keep what is red, orange, and the rest is the background. So that is thresholding. Now, what we want to do is to say what percentage of those black pixels belong to big holes, medium, small, or tiny holes. So basically, we open that image with a big structuring element that we choose, and that will be the size, the minimal size of what I called a big hole. So if I want to say a big hole is all the holes that are bigger than that, I choose a structuring element of that size, I open my image with that, and what will remain is that it will be all the objects bigger than that. What will disappear is all the objects smaller than that. Yeah? So you get first part of your answer. You know how many pixels, or what is the area of the big holes. And then you do the difference. You say this image is just the rest. The pixels that are here, I don't count them. They are not here anymore. But all the others are still there. No. Yeah, first you just do the difference. And then you reopen. That one? That one is the opening, yeah. The opening of that. Then you get that. You do again an opening, but with a smaller structuring element that you choose, which is the typical size of the second part of your analysis. You get that. You count, difference. Open, count, difference. And then you get your distribution by size, not by pixels anymore.
could you just pick the structuring element that's for the smallest acceptable hole and that is not noise?
Yes.
And do region growing on the whole picture to say this is a hole, this is a hole, this is okay.
But they are connected.
Yeah, yeah,
Look, many of them are connected. Here, with the mathematical morphology, you choose by size. So whether they are connected or not, you don't care. That's one of the applications of mathematical morphology, and that's what I wanted to show in this last slide. If you have objects that touch each other, a way to separate them is to erode, and that's an application of just erosion and dilation. The question to your question. If I erode them, they will separate apart from each other. And at some point, they will only remain a point, and at the next iteration, it will disappear. But if you stop just before they disappear, and you mark them just before they disappear, you will end up by identifying the centers of the three objects, even if they overlap, and manage to count how many objects you have, even if they overlap. And that's a very powerful method, which is called the ultimate eroded. Ultimate eroded. You erode until a region disappears. And if it disappears, you do one step back, you mark it as the center of an object. And you keep doing that for all the islands that are created by the erosion, and each island will be actually becoming ultimately the center of one of your original image. And that's very nice. That's a very nice technique. Okay? Questions? What time? Yeah, it's okay. We still have time for questions, yes?
In granulometry example, well, I don't understand why we use opening, but not just erosion. Because with erosion, we will just get...
Yes, but with erosion, you would basically get smaller versions here. Yeah. What I want is to calculate the area of the holes. So if you calculate the area of the eroded, you underestimate.
Yeah.
But you could, huh?
Okay. I just didn't get that we want area. I just think that we need just
to come.
Components are like larger or not.
Well, yes, but again, if you only do the erosion, you cannot do the subtraction after, because the difference between the original and the eroded, you will get a ring around your objects, right? If you want to count how many pores, how many holes you have, then you can. Because to count how many holes you have here, you would do what we explained before. You would do erosion until it disappears. So each of them will basically shrink. They will split apart from each other. And then each time you have one that disappears, you say, okay, this is one of my objects. I step back, I mark it, and I keep eroding the others.
But opening also.
But opening, yeah, of course. But here opening keeps the size. So since I'm interested in the size, I prefer opening. You see that you have to use those methods in a kind of a clever way. You have now a toolbox, and you have to use the tools. There is no unique answer to a given problem, and no unique answer to many problems. You have now a toolbox. And that's what I wanted to say in this course, and that will be my conclusion. This is all I will say about segmentation. So 2 hours or 3 hours about segmentation only is very little. But I hope now you have a toolbox. And now your job as image processing specialists is to use those tools for a given problem. And next week we'll see more about next time we'll see more about features and classifications. These will be tools that you will have in your toolbox, and then your job as designers will be to use those tools to solve a problem. I will never see a unique recipe for solving all the problems. Even machine learning doesn't do that. Okay? More questions? Yeah. 24.
How can the Gaussian filter help us? Because we want to find the zero crossing. What's the purpose of the Gaussian?
So the zero crossing, we want to find it, because this is where the edges are. The Gaussian is just a way to select which edges I want to keep. Do I want to keep all the edges, including the edges of the noise? Do I want to keep all the edges except the noise, but also with the small objects? Or do I want to keep only those very big, sharp edges? And I have this margin, this flexibility. And this is exactly what it does. The Gaussian allows you to choose the range of frequencies. In this case, it is really frequencies that you want to keep.
It's just for to not consider the effect of noise.
Or other. What is noise? Noise is what you don't want to see. So in this case, you can choose, it's right, the Gaussian will remove the noise, but you can choose what you mean by the noise. By tuning this sigma, you can choose that those small edges that I have here, for you, it might be noise, because you're interested in what I say. But if you want to read, this is not noise anymore. Well, this might be, but that's not. So you choose the parameter, and you define what you keep and what you get rid of. Okay? So I think I'm done for today. Thank you very much for being here. We will see you in 3 weeks for the lecture. 2 weeks will be the first lab. Next week, 2 weeks, the first lab. It's recorded, so I should not say it. 2 weeks, the first lab. 3 weeks, the lecture on active contours, if I'm not wrong. Check on the Moodle. Stay tuned on the Moodle. Ask your questions on the Moodle, and we will answer. Have a good week. See you soon.